Hello viewers, welcome back to my channel. I hope you are enjoying all the problems that I am uploading. If you haven't subscribed to my channel yet, please go ahead and subscribe. Today's problem is balance a binary search tree. Given a binary search tree, return a balanced binary search tree with same node values. A binary search tree is balanced if and only if the depth of the two subtrees of every node never differ by more than 1, right? So the definition of the balanced binary search tree is the depth of the two subtrees of every node never differ by more than 1. If there are more than one answer, return any of them. So basically we are given an arbitrary binary search tree. So remember, it's a binary search tree as well, but it is not actually properly balanced. So now we are asked to return a balanced binary search tree. So the definition given here is the depth of the two subtrees at every node should not be more than 1. So the heights of the subtrees at every node should not differ by more than 1. That is the definition given here, right? So in the example 1, right, so 1 2 3 4, so this is a right skew tree with 4 nodes, right? So what could be the possible things when we are just given with 4 nodes, right? So we say, okay, there are so many possible trees for this, right? So we could say, we could start with a 2, right? We could start with a 2, and then on the left side we say 1, and to the right side we say 3, and we go 4. So that will be, so although it's not greatly looking in this way, so 1 2 3 4, that's a balanced binary search tree, right? So this is better balanced. So this is one of them. So there are several possible balanced binary search trees. So we were asked to give one, right? Any of them is fine. So this is one of them. So if you have to write one more, right? So we could say, okay, 3 is the root. I'm going to make 3 as a root, and 2 will be my left subtree, and 4 will be my right subtree, and 1 will be left subtree for 2. So at every level, right, the height of the subtree is differing by 1. So if you say at 3, right, so what is the height of the left subtree? It is 2. Right subtree, it is 1. So 2 minus 1 is 1. So for 2, left subtree is 1, right subtree is 0. So 1 minus 0 is 0, right? So for 4, anyway, there is no left subtree, right subtree. So the difference between left subtree and right subtree at every node is maximum of 1. So that is valid for this subtree as well as this subtree also, right? So that's how we have to build from this tree, right? 1 2 3 4 in the example 1. So likewise we were given with several examples, right? So this is one of the answer. So that's 2 is the root, 1 left subtree, 3 is right subtree, and 4 is right subtree for 4. So that is actually my first solution, right? So this is another solution. So there are so many solutions possible, right? But we are asked to give one of them. So what we are going to do for this problem is, essentially, in order to construct the binary search tree, we need to know all the nodes, right? So for that purpose, I have devised a two-step algorithm here. So in the step 1, we are going to gather all the values from the binary search tree, right? So gather all the values into an array or list and use that to construct a binary search tree again, right? So you use that to construct the binary search tree again. So that's what we are going to use. So my two-step is, first get all the values from the given tree using the Inorder traversal of the array. So when you do Inorder traversal of the array of the binary search tree, right, that is going to give all the elements in this tree as in a sorted order. So since it is a BST, right, Inorder traversal will give you the elements in a sorted order. So once you have the elements in sorted order, right, it's very easy or simple to construct a binary search tree in the using the array. So once we construct that array, just return it, right? So this is the method that we are going to use essentially. So Inorder traversal and binary search tree construction. So we are going to have two different methods, okay? So two different functions. So here balance BST, we are passed with a root node since we don't know how many nodes are there in that particular thing, right? So we are going to create a list, right? So list of integer, I'm calling it as array though. So this is a list and pass that list to the Inorder traversal by passing the root. So Inorder traversal is a simple Inorder traversal that I wrote. So this is basically a recursive Inorder traversal. So if the root is not equal to null, then only we proceed. So let's look at Inorder traversal order. So Inorder traversal is, it will go to the left and then it will do the root and then it will do the right, right? So that is the order. So Inorder means it will go to the left subtree and then look at the root and then look at the right subtree. So this will be called again and again in the recursive fashion. So in the same way that I have the recursion, right? It's pretty simple. So Inorder traversal, go check the left subtree and look at the root value and go check the right subtree. So this is the very basic Inorder traversal, right? So with this, it will get me all the values in a sorted order in the array, right? So now that I have this, what I'm going to do is go construct and return whatever the output that I get from the construct. So for this, I'm going to pass the elements and the 0 and count, basically how many elements are there, right? So let's go ahead and look at the construct binary tree function. So this is also very easy implementation for the construction of the binary tree, right? So we were passed with an array and a start and end, right? So from where to where the elements we are going to use. So we will be doing as long as our start is less than or equal to end. Once start and end flip, right, then we are going to return null. So we have already constructed, that means, right? So as long as start is less than end, we are going to construct. So we are going to say mid. So mid is start plus end by 2. So whatever the middle element in the array, right, that will be our root node. Whatever the middle element in the array, that will be our root node. That means what we are saying is on my left subtree and on my right subtree, there will be almost equal number of elements, right? So that is what midpoint is, right? So when you say midpoint, the definition, it is understood that the left subtree and right subtree will have almost same number, right? It's not, we are not saying exactly same number because there can be even number of elements, right? That's why we are not saying they are equal. If there are odd number of elements, obviously we'll say, okay, there are equal number of elements on left subtree and right subtree. So just like in our previous example, right? Here there are 4 elements. So here on the right subtree for 2, there are 2 elements, and the left subtree there is only 1 element, right? So that's the reason why, even though you split at the midpoint, right? Since it is a tree, binary tree, the number of elements in the left subtree and right subtree are not same exactly, but they differ only by 1, that is at most by 1. So we are still following that definition, right? So we are still following this definition of balanced binary search tree. So it still holds good with our logic so far, right? So mid will be our root node. So what we are going to do is, until mid, the element should go on to the left subtree. After mid, the element should go on to the right subtree. So we are going to do exactly the same thing. So onto the left subtree, we pass the array and go from start to mid minus 1. because mid is already used here, right? Mid is root, and for right subtree you go from mid plus 1 till end, right? So that is what construct we are calling it recursively. So this will be called recursively, and finally what we are going to return is the tree node, right? So whatever the constructed, the root node, that we are going to return. So finally, since we are returning this method's output itself, right, it will return the tree node as the answer for us. So let's go ahead and look at the time complexity and space complexity for this algorithm, right? Right. So time, right? So time, how long we are going to use do the Inorder traversal, right? So we have to traverse each and every node. Let's say there are n nodes in the binary tree. So the time needed is to traverse n nodes, we will say n nodes, order of n, right? Plus we are doing something else, construct a binary tree. So since there are n nodes and we are trying to rebalance the binary tree into n nodes again, right? Obviously we have to visit each node again at least once. So that means we are doing order of n here and order of n. So this total will be order of 2n, right? Order of 2n. Sorry, 2n. So since we omit the constants in big O notation, right? So what we will say is order of n. So the time complexity will be equal to the order of n nodes, right? So that's the time complexity. So for the space complexity, so we are using a space of array, right? This is equal to the order of the order of the number of nodes again, right? So since all of them are integers, right? So the list length, the array length here will be equal to order of n. So but there is more space that we are using, right? So here we are constructing the tree node. So if you say, okay, we are throwing away the given tree and reconstructing this tree again, right? So again, order of n, there will be n nodes, right? So we are saying each node will have node value plus 2 pointers also, right? So in that case, what we are going to do is there are 2 pointers, so those are constant things that we are going to use. So n elements, so that will be order of n elements plus each element or each node will have its own value plus 2 pointers. So 2 pointers, assuming that there are anyway n pointers that need to happen, right? So if you were given n nodes, there are n minus 1 pointers, right? So from 2 to 1 and 2 to 3, so that means 3 and 3 to 4, right? So there are 3 pointers for 4 elements, although there are null pointers, right? So if we have to count null pointers, there will be 2n pointers totally, right? So n plus n pointers. We just for the worst case, we want to consider null pointers also, right? You can say 2n pointers. So that will be totally order of 4n space, right? So if you omit all the constants, it will be the order of n space complexity also here. So the time complexity is also order of n and space complexity is also order of n in this particular case. So please note that the node, whatever the definition that we are taking, so the node definition is this, right? So I am taking it as constant thing, basically value plus 2 left pointers, right? So value plus 2 left pointers. So that will be, I am taking it as 1 unit, okay? That's why I am saying n units of space that I need. So it could be, if you represent each node is going to take m units, since I said only 1 unit, right? If it is saying m units of space, right? In other words, each node takes m units of space, right? M units of space, right? In that case, what we are going to say is order of mn, right? Each node, right? Order of mn, right? That is the space complexity, you can say. So that is the overall. When I said order of n, I was considering m as one unit of space. But if you think m is the unit that we need to actually makes more sense or appropriate, right? So the time complexity will be order of mn, right? So that is how it is going to look. If you have any questions, please post them in the comment section below the video. And also, if you haven't subscribed to my channel yet, please go ahead and subscribe. And also share among your friends. Please don't forget to click the bell icon. If you click the bell icon, you would get notifications about all my future videos. Thank you for watching. I will be back with another video very soon. Till then, goodbye.